Hi everyone, I am Nusret Tas and I'll be talking about vector commitments with efficient updates. This is joint work with Professor Boneh at Stanford University. So before I talk about the importance of efficient updates for vector commitments, I would like to start with an application of the vector commitments in the blockchain space, which is the stateless clients idea. So let's consider a blockchain that keeps track of the account balances of its users. So this vector of account balances constitutes the state of the blockchain, and the state is persisted in the form of Merkle trees. Now, the Merkle root of the tree is also known as the state root and is typically included in the block data. And when new transactions are appended to the blockchain, this vector of account balances and the corresponding Merkle tree is updated to reflect the effect of these transactions on the state itself. Now, these Merkle trees or the states, they are persisted by the blockchain validators that update the state and the Merkle tree. On the other hand, we have clients, each of whom might be interested only in its own account balance within the state, and it only maintains its own Merkle proof for the account balance. So in this example, we see the account balance of a client I as a leaf of the Merkle tree, and we see the corresponding Merkle proof. Now, when there has been a lot of updates in the blockchain with appended transactions, the clients need to also obtain a new Merkle proof so that they can verify the inclusion of their account with respect to the latest state root. To help clients update their Merkle proofs, the validators can generate what I would like to call an update information, denoted by U, and make U public. So this you can think of it as being included as part of the blockchain transactions, blockchain data. On the other hand, besides U, the clients already do have access to the information of how much was changed in the account balances of the other clients by looking at the transactions. So they can use this public knowledge as well. And combining this update information U and the message diffs, this knowledge in the change of accounts, each client can update its own Merkle proof. Now, the validators are interested in minimizing the size of this update information U as much as possible because this is an overhead for them on top of maintaining the transactions in the blockchain. On the other hand, the clients are interested in minimizing the time it takes for each client to update its Merkle inclusion proof as much as possible. So now this tension begets the question, what is the smallest update information size and the proof update time that can be achieved, right? And in particular, can we achieve a good size and good update time by replacing Merkle trees with some other vector commitment, perhaps, to persist the state? And before I answer that question, I would like to give a brief introduction to vector commitments. So they are characterized by typically 4 algorithms. So the first one is the key generation algorithm that takes in a security parameter and the size of the vector, and it outputs some public parameters. So all of the following algorithms will be parameterized by these public parameters. The second and the most well-known one is the commit algorithm that takes as input a vector of messages and outputs a commitment to this vector, so the name the vector commitments, and some auxiliary data. Now, when a client wants to obtain the opening proof for its message at a certain index, it calls the open algorithm. And then the validators, for instance, use this data to generate for this message the opening proof of the message. And then the verify algorithm takes as input a message at some index I, the opening proof for it, and a commitment, and it verifies the opening proof with respect to this commitment. Okay, so we have these 4 algorithms. What we would like to satisfy with these 4 algorithms are the 3 properties. The first one is correctness, that states that if the opening proof is generated correctly through the open algorithm, then it verifies. The position binding states that the adversary cannot open a single commitment to 2 different messages at the same index that would verify with opening proofs. And succinctness states that each opening proof and the vector commitment are both succinct, namely at most polylogarithmic in n. So that will be the succinctness definition I would use. I will not focus on the hiding property in this talk. So for a vector commitment to be used as part of the stateless client's paradigm, we would like it to be also dynamic or updatable. So updatable vector commitments have 2 more algorithms. So the first one is the update algorithm run by the validators. So here we see a commitment to a vector of messages and the corresponding auxiliary data. when some of these messages are updated, the validators look at the message diffs that are recorded in the transactions and the old auxiliary data they have, and then they update the vector commitment and the corresponding auxiliary data. And in the process, they also generate the update information. Now, on the other hand, we have clients who run the proof update algorithm to obtain the new opening proofs. So here is a client that keeps track of the message at index I, and it has the old opening proof that verifies with respect to the old commitment. It has access as public information to these message diffs and the update information. And using all of those through the proof update algorithm, it obtains its new opening proof that verifies with respect to the new commitment. Okay, so we have seen how dynamic vector commitments are, and now let's see how they perform in terms of the trade-off between the size of the update information and the runtime of a single opening proof update. Now let's suppose k messages are updated. Okay, so let's see how the existing dynamic vector commitments perform. On one hand, we have the tree-based vector commitments. Typical examples are Merkle trees or the Verkle trees. So if you haven't heard, Verkle trees is the proposed design for Ethereum's stateless client. So these actually enable clients to update their opening proofs in constant time that doesn't depend on the number of updated messages. However, they have to publish a large amount of update information that scales linearly in the number of updated accounts. On the other hand, we have algebraic vector commitments, such as KZG commitments, RSA-based vector commitments, bilinear accumulators, and so on. So these actually don't require almost no update information. However, they require each client to take into consideration every message update at every updated message. Now, in our work, we can basically interpolate between these two, and we can achieve what I would like to call efficient updates by achieving an update information size and proof update complexity that scales as shown, as long as their product is equal to the number of updated messages. And furthermore, we show that this trade-off is optimal. You cannot beat that trade-off via an information theoretic lower bound. Okay, how do we achieve this? So at the heart of our construction lies the idea of a homomorphic tree. So a homomorphic tree is characterized by a homomorphic partial digest function that calculates the effect of a message on the inner nodes that lie on the path from the message to the root. So here we have n equals 4 messages, and suppose the inner nodes are some group elements, right? So each inner node is calculated through the homomorphic partial digest function as a sum of the effects of the messages that lie under that inner node. So this characterization, in particular the homomorphic nature of this partial digest function, enable us to update the inner nodes when an underlying message is updated purely as a function of the message difference. So here how it goes. So suppose the message M1 is updated to be M1 prime. In this case, this circled inner node, it is updated as by simply adding to the old value of the inner node the function h12 applied to the message diff. So h12 is the effect of message 1 on the inner node that is removed by a path of length 2 from the root of the tree. And the same goes on for the for some higher level inner node, and the same goes on for the root as well, and so on. Okay, so this is how homomorphic trees can be updated. So what is special about homomorphic trees? We basically design a system where we can achieve vector commitments with these efficient update properties if the vector commitment is based on a homomorphic tree such that the opening proof of the vector commitment can be calculated as a function of the inner nodes that lie on the path from a message to the root and their siblings. So here, we require the opening proof of message M1 to be a function of the nodes on the path from M1 to the root and its siblings. And these are the circled nodes, the ones circled with red. Okay, so are there vector commitments that satisfy this property? Well, there are existing ones that do. So here are some examples. But we are not done yet because I haven't yet told how we generate the update information. So we use the homomorphic tree to generate the update information via a special algorithm. And now I will talk about how we generate the information. So suppose k messages are updated in total, so our algorithm starts at the root of the homomorphic tree, right? So it looks at the two children of the node, which it starts at, which is the root, and it asks the question, is the number of updated messages greater than k to the 1 minus nu under the left child? If the answer is yes, then it basically includes the new value, the updated value of this inner node as part of the update information, and it keeps recursing under that node as if it is the root of a tree. And it does the same for the right child. It asks, is the number of updated messages greater than k to the 1 minus nu? The answer is again yes, so it includes the new value of this inner node that is higher up in the tree as part of the update information, and it recurses there as well. So we continue. We look at now the left and the right children of the left child of the root, right? So under this left child, there is again more than k to the 1 minus nu updated messages. However, on this right child, there is not more than k to the 1 minus nu updated messages. So we do not include it as part of the update information, and we do not recurse anymore. The algorithm basically stops there. And the same goes on for the right child. Okay. Now, with this algorithm, we can basically achieve an update information size complexity that scales as k to the nu, and a runtime complexity for proof updates that scales as k to the 1 minus nu. All right. Okay, so far I have only been talking about asymptotics. Of course, everyone is interested in concrete numbers. So how the existing vector commitment schemes combined with our algorithm and characterization perform. So I listed 4 of them here. So the 3 of them are lattice-based, and the 4th one is a pairing-based one. And they all, if you squint them hard enough, they all rely on a homomorphic tree. So again, they are asymptotically, they can achieve asymptotically optimal update information and proof update time. And how do the estimates look like when we, let's say, have a vector of 2 to the 24 elements, and when 460 of these elements are updated? So these numbers look quite random. They are not quite so random. So 2 to the 24 was selected to be on the same order of magnitude as the Ethereum state size. And k equals 460 is some back of the envelope calculation of how many ERC20 token transfers you would have in a typical Ethereum block if you fill it up with these transactions. And here are some group element sizes and the hash value sizes. And now for the construction 4, when we set this new parameter to be 1/2, so that we have square root k complexity for the update information and proof update time, we achieve these numbers. So for comparison, I attached the number for vertical trees with a degree of 256. Note that for the vertical trees, they lie on the top left of this graph that I have shown. So for the vertical trees, the update information time is very short, asymptotically. However, their update information size grows quite a bit. The U scales linearly with the number of updated messages. And we can see that the construction 4 actually can beat the vertical trees even in concrete numbers, not necessarily asymptotically. Yeah, vertical trees are not asymptotically optimal in that sense. And the construction that relies on lattices has large values, large lattices, so it's not as performant. Finally, I would like to talk a little bit about the lower bound. So our lower bound applies to vector commitments that satisfy a special property that I would like to call proof binding. Although it's not that special, almost any vector commitment that you know of satisfies this property. So this property says that it's hard for an adversary to find 2 sequences of messages that needs to disagree at least one message. But suppose these 2 messages agree at an index I. So at index I, the messages are the same. And then the adversary finds basically a single opening proof, which is pi I, such that this pi I verifies for the message mi at index I where they agree with respect to the 2 different vector commitments. Note that the vector commitments must be different because the sequence of messages differ at least one position. So this is actually synonymous with the fact that the opening proof itself acts like a commitment to the remaining messages other than the message that we are finding the opening proof for. Okay, so almost all vector commitments I know of satisfy this property. And we basically show that let VC be a dynamic vector commitment that is proof binding and also position binding. Position binding is one of the earlier properties that we have seen. So if K messages are updated and we require the update time for a single proof update to be less than K to the 1 minus nu, then the size of the update information is going to be greater than K to the nu for any nu between 0 and 1. Okay, so this is the statement of the lower bound. And so we have constructed an update algorithm that is asymptotically optimal. So in the paper, you can see the update and proof update algorithms for the Merkle trees as well, through which we generated these numbers that was on the construction slide, and also the way we estimated them. Thank you.
Thank you for the talk. We have time for some questions. I have one while they think for some questions. So have you talked to the Ethereum developers about this result? And if so, what they told you about it?
We haven't talked to them yet because the more optimistic results came actually a bit later than the earlier ones. So initially, we were only aware of like 3 constructions that were lattice-based that had this homomorphic tree property. Then we found basically another one that was published, I guess, still in 2020, but we weren't very much aware of the construction that had also this homomorphic tree property. And that one, because it's based on bilinear pairings, not lattices, it's much more efficient. So only then we had the more efficient results for that beat the Merkle trees in estimation. Of course, these are just estimates, so I guess an actual implementation demonstrating them would be also preferable.
Thanks.
Do you have any trusted setup for this pairing-based result?
Yes, the pairing-based result requires trusted setup. The lattice-based one, I am not sure. It doesn't require public parameters that are large, that is for sure. The pairing-based one, in order to use our update algorithm, it requires public parameters that are somewhat large.
Do you know if it's the same kind as a KZG setup?
Yeah, the setup will be the same as the KZG setup. The size of the public parameters will be also the same as the one that will be required by the Merkle trees.
Okay, so one last question. If not, let's thank the speaker again.